So what we're going to do here is rewrite that 2x to the fourth minus 1. We're going to rewrite it accounting for every possible exponent from a power of 4 down to a power of 0. Right? So in this case, we're going to say 2x to the fourth. There's no x to the third there, so it must have had a coefficient of 0. There's no x to the second, so that must have had a coefficient of 0 also. There's no x to the first, so that must have also had a coefficient of 0. But then finally, we have that -1. That would have the assumed variable raised to the 0th power, in this case, variable x. Okay. So as long as you account for every exponent from whatever the highest exponent is in your polynomial down to 0, you'll have accounted for every coefficient. And then what we do is we strip it on down to just the coefficients. So 2, 0, 0, 0, -1. Okay. Then separately, we take our denominator and set it equal to x minus r. Subtract the x from both sides, cancels out. You're left with -4 is equal to -r, which means 4 is equal to r is equal to 4. That's the number that goes on the outside. All right, it's the outside of your synthetic division bracket. All right, so I'm going to put the 4 on the outside. Then I'm going to bring down my coefficient here. I'm going to multiply it by the 4 on the outside, and that's going to give me an 8. Then I'm going to add. All right, so we're always adding down the columns. So 0 plus 8 gives you an 8. Then I'm going to multiply that number by the value on the outside. That's going to give me a 32. I'm going to add down that column, which is going to give me a 32. Then I'm going to multiply. Gets a little out of hand pretty quickly. I'm going to multiply by the 4 on the outside, which is going to give me a 128. I'm going to add down the line here. That gets me to a 128. Then I'm going to multiply that by the 4 on the outside. I get a green involved here, I think. All right, so 128 times the 4, so times 2 is what?
512.
It's 511 or 512, 512.
Yeah, 5. $512, and so the sum down the line there is going to give me 511. That last entry is our remainder. We take the power that we started with, reduce it by 1. That's going to give us the power, or at least the starting power for our final answer. So x to the third. All these numbers are positive, so I'm going to tuck in little plus signs here. All right, we start with the power of 3, x to the third, and we go x to the second, x to the first, and x to the 0th. But you don't really need to write the x to the 0th, it's going to go away anyway. But this would give us a result of 2x to the third plus 8x squared plus 32x plus 128. Then we tack on to that remainder divided by whatever the divisor was. The divisor was x minus 4. All right, the remainder always gets divided by the divisor, and that would be your result. That would be your quotient. Now you look at this and you say, all right, that can't be right. You know, like there's no way. So you check your work. Okay, so you type in the original ratio. Oops. 2x to the fourth. You could write it as y equals, but you could also write it without the y equals. It'll graph it as if it's a function anyway. And then, you know, it's a fair amount of typing, but if you want the confidence of knowing that you did it correctly, then it's worth taking the time. Plus fraction 511 over x minus 4. And it maps to the same location, right? No matter how hideous it is, this graph and this graph are mapping to the same location. So we're confident that we did it right. And again, if you have a hard time making the judgment, you know, just change the parameters of the graph, make it a little thicker, make it a dashed curve instead of a solid curve, so that you can see that they're definitely overlapping with one another. And it makes it a little bit easier. But that would be your final answer. All right. But the presence of the remainder here tells us that x minus 4 is not a factor of 2x to the fourth minus 1. Whereas in the previous example, we had a remainder of 0, which tells me that x minus 4 actually is a factor of 3x to the fourth minus 11x to the third, blah, blah, blah. All right. So just by determining whether there's a remainder, you can get an idea of whether your fraction is something that can be simplified in a reasonable way. All right. So we're going to apply this in a couple of minutes, but before we do that, I wanted to show you something called the remainder theorem. It's a required topic, but it's very, I don't want to say it's archaic, but it's the kind of topic that you kind of look at and say, I'll never need to do this because I can always just use a calculator. I guess until the time where you're not able to use a calculator, right? I put this firmly into the category of just, I'll call it cool math. Right? It's just an interesting thing that occurs mathematically, and it's kind of something that maybe you don't expect would be useful, but then every now and then it comes in handy. And you're like, oh, I applied that one thing that we did that one time, you know. So we have this function f of x is equal to, and we get all the coefficients. The remainder theorem is telling us that the remainder after the synthetic process, the synthetic division process, will help you to determine, or actually will determine for you, the result when you evaluate a function, right? So evaluating a function, if you remember, that's you plug in a number into the function and simplify, and you get an answer. The remainder theorem will give us that also. And oftentimes, with a fairly complicated looking function, it'll give us a pretty reasonable answer, or at least it'll give us reasonable computations to get our answer. So looking at this, what we would do is it would be the same setup in terms of coefficients and stripping down, removing all the variables. So I'd rewrite this as 4x to the fourth plus 10x to the third. We're missing a power of 2. So I'd say plus 0x squared plus 19x plus 5. And like I said, we just strip this down to just the coefficients: 4, 10, 0, 19, and 5. Now, what this is telling us is that if I want to compute something like f of 3, right? Now you just think back to the first unit. F of 3 we would get by replacing all the x's with a, I'm sorry, f of negative 3. Replacing all the x's with a negative 3 and simplifying. What I'm saying is we could also do it with synthetic division, right? Which is to say, all I would need to do is put that negative 3 out on the outside, that's fine. On the outside of the synthetic division. So whatever is contained within the expression to be evaluated gets put on the outside. Then you run through synthetic division the same way we did up here. Multiply, add until you run out of space. I take my 4, I multiply it by the -3. I get a -12. I add the results. I get a -2. I take that, multiply it by the value on the outside, get a result. -2 times -3 is +6. Add. Result is 6. Take that, multiply it by the expression on the outside. Going to bring orange back into the fray here. 6 times -3 is -18. Add 19 plus -18 is a 1. Oops, I want to go with the black pen there. And let's see here. What have I haven't used blue in a while. So I use this kind of blue, whatever that color is called. Multiply on the outside, result on the inside. 1 times -3 is -3. Add. And you get your remainder. Now there's a reason why it's called the remainder theorem. Because in this context, the remainder is your answer. All right. So this 2 is the result of f of -3. All right. And I could show you really quickly on Desmos. And you'd be kind of right to think that's kind of pointless. Why would we ever do it that way? Because I'm about to show you the way that most people would normally do it. It use technologies in some way, shape, or form. But you know, the easy answer is like you might find yourself in a calculus class where your teacher is like, you can't use a calculator. All right, so this would be a good resource or a good strategy. That being said, if you find out that a teacher's not letting you use a calculator, you're probably going to be like, all right, well, I'm not going to take that teacher. So I mean, there's ways around it. So my reasoning is somewhat askew here, but f of 2, if I just type it in, I'm sorry, f of -3, I get a result of 2, just like we got with the remainder theorem. All right. So it works. It's a technique that works, and it allows you to avoid having to work with really large numbers. Right. Because if you were to substitute a -3 in here, you'd get an 81. You'd then have to multiply. If you're doing it by hand, you'd have to multiply the 81 by a 4. You'd have to take that -3, cube it, and you get -27, multiply that by 10, put it all together. The numbers get pretty large and kind of out of hand. But this is a nice way to sort of keep the values small. Mm-hmm. So the way I do it on a test, if I ask people, if the question comes up, and I kind of haven't really decided if it will for this semester, I have asked it in the past, but I'm not 100% sure if I'm going to do it this semester. But if I were to put this on a test, it would be along the lines of show that f of -3 is equal to 2 using the remainder theorem. Right? I wouldn't be looking for the answer. I'd be looking for you to show that you could use the remainder theorem to get the answer. Right? So a little bit different. So in order to get to the next part of the unit, we need to review some old stuff. Right? Complex numbers, and also known as or not also known as, but part of the fundamental theorem of algebra. You wouldn't think that you'd have to get this far in order to get to the fundamental theorem of algebra. You think that would be one of the first things that you learned, but if you look at the definition of the fundamental theorem of algebra, it's not the sort of thing that a first semester math student would really be able to comprehend. You wouldn't have the skills yet. Every complex polynomial in one variable and degree n greater than or equal to 1 has some complex root. All right. That's a mouthful. And it doesn't mean anything if you don't know what a complex number is. All right. I included this diagram here to remind you what complex numbers are. You have your set of real numbers. This bothers me. Okay, that's fine, I guess. All right. You have your set of real numbers. Those are made up of rational numbers, integers, whole numbers, natural numbers, and also irrational numbers. Then you have your set of imaginary numbers. The imaginary numbers, if you remember, involve negative under a radical. All right, but specifically even radicals. All right, so that's square roots, fourth roots, sixth roots, and so on. There's nothing wrong with having a negative under an odd radical. So if I had something like the square root of -2, says undefined by Desmos' standards. But if I say the cube root, which would be the same as raising it to the 1/3 power, I get a real number. I don't get an undefined. So it's perfectly okay. Complex numbers have a real component. So when I look at complex numbers, a plus bi, this a represents the real component. And the bi represents the imaginary component. Right, and that's because I is equal to the square root of -1. Right. So any imaginary number can be written as a multiple of I. For example, if I had the square root of -4, something very simple. If I have the square root of -4, I can break that up into the product of -1, the square root of -1, that is, and the square root of 4. All right, the square root of -1 would become the I, and the square root of 4 would become a 2. Put them together, and you get 2I. All right. All right, so that's old stuff, but it was worth talking about because people tend to forget that sort of thing. All right. Because in college algebra and even classes before that, it comes up, you do stuff with it, but then it goes away. And you don't really look at it again until the next course where you touch on it again a little bit. Then it goes away. And actually, it'll disappear for a much longer stretch after this course. You know, you're talking like Calc 3 differential equations. So, you know, it is what it is. It's kind of a flaw in the system, but it's part of the curriculum, so we got to do it. So a complex conjugate, to review that concept, if you're given a plus bi, the conjugate is a minus bi. If you're given a minus bi, the conjugate is going to be a plus bi. All right. So a consequence of that is really it's a rule, but it's more like, I would say it's more like something to be on the lookout for. Complex roots occur in conjugate pairs. So if I know, for example, one root of a polynomial is 3 minus 2i, and I'll actually write this down. I'm going to shrink it down a little bit. So, for example, if we know a root of a polynomial is 3 plus 2i, then another must be 3 minus 2i. All right. Those are conjugates of one another. If you haven't picked up on it, conjugates are the same terms, just with a different sign in between. All right. Both of them have a 3. Both of them have a 2i. It's just one has a plus and the other has a minus. That's how we denote conjugate pairs. All right. And they're complex conjugates because they involve complex numbers that are in the form of a plus bi. Now, that is helpful, at least you'll see that it is. A rational roots theorem is, if we go back to the remainder theorem from the previous page, and kind of goes hand in hand with that in the sense that in a lot of ways it's sort of archaic and outdated. I guess that's the definition of archaic, but we don't really need it with technology. But it might come up down the line, so I figured I'd go over it and give you a sense of how it works. All right. The blurb here, I mean, I did my best to write something that actually makes sense, but even still, it doesn't always make perfect sense. So it'll make more sense with an example, but I'll read it to you anyway. Possible roots are equal to p divided by q, where p represents the factors of the constant term and q represents the factors of the leading coefficient. Okay. Then you have the process, which tells us to use the rational roots theorem to find potential roots. Potential being the key word there, not guaranteed. Oops, helps to highlight the right word. These are values that could be roots. We'll use synthetic division to investigate and determine whether they are actual roots. And then we'll see if we can get our original polynomial down to a second degree polynomial, degree 2, because once we do that, then you have other methods for finding roots, factoring, completing the square, and quadratic formula. Most people prefer the quadratic formula, mostly because they tend to forget how to do completing the square. All right, before the course is over, you'll have to know how to do completing the square. It doesn't have to be now, but it's definitely something you should take some time to review. But we'll review it down the line in class also. All right. So what we would do here, if you look at the instructions, right, each of the following is a product of first degree factors and find the roots. Not really giving us much in the way of instruction. It's saying, it's basically telling us to factor this cubic. So what we do is we look at the leading coefficient and we look at the constant term. The constant term is the term that doesn't have a variable attached to it. All right. That constant term, we call that P. I don't know why. I would call it something completely different, but every textbook in creation calls that P. So at the risk of, well, to avoid risking confusing the living daylights out of people when they go looking for this online, other resources, I'll just go with the standard way of representing it. The leading coefficient we call Q. And so what we do is we list the factors of P, and we list the factors of Q, all possible factors. Okay. So we're thinking about any number that could divide evenly into 36 and any number that could divide evenly into the number 1. Well, the number 1's easy. It's 1 or negative 1. So I say plus or minus 1. 36 is a little bit more complicated, but still manageable. You just go down the line and say, all right, I got to multiply to 36. Will 1 divide evenly into 36? Yeah. Will 2? Yeah, 36 is an even number. And if you're not sure, there's a couple of ways that you could do it on Desmos, but the simplest way would be to say 36 divided by 1. Okay, that works. I get an answer. By answer, I mean whole number answer. By 2, okay, we're good there, whole number. By 3, whole number, good. So 2 and 3, those are fine. 4, yeah. And indirectly, we're getting other factors because I now know that 9 is a factor if I didn't happen to know that 4 times 9 is equal to 36. All right, 5, decimal value, so ignore the 5. 6 is good. 7, no good. 8, no good. 9 works. Right, the no goods are the ones that involve decimals. So 10 is no good because I got a decimal value. Same thing with 11. 12 is fine. 13 is no good. 14, 15, 16, 17, 18 is good. And then you can skip everything right until the 36, because if you think about just division, if you divide a number by anything more than half of its value, you're automatically going to get a decimal. That being said, if you did this correctly, then you should have symmetry, as in the first and last values, the second and second to last, the third and third to last, fourth and fourth to last, should all be factor pairs of 36. All right. So that's one way to do it. Very tedious. I always felt like that was sort of a bittersweet moment when the teacher would acknowledge that what we were doing was boring, tedious, etc. It was good. Oh, he's on the same page. He understands. But then the other part is like, so then why are we doing it? Like, again, like I said, folks, I mean, and it's very rare that I say this. This topic is being covered because it's a requirement for the course, and you may need it in the course down the line. But if I had my druthers, I don't even know what a druther is, but if I had one of those, I would eliminate that from the course. Right? But
So what would you even use this for in real life?
We use it to find roots of polynomials. So it's a skill helping us to find the roots of polynomials. The polynomials themselves have a lot of different applications in real life.
Right.
So this is really just a method to evaluate the thing that has an application in real life. Yep. Oh, and it gets better. It gets better. So what we would have to do now is take each one of these p values and divide it by each one of the q values. So we create a list here. So each one of these p-values divided by each one of the q-values. Now, fortunately, there's only one q-value. So regardless of how I do this, I'm gonna come up with the same list of values that I have in P. All right. All right. So this would be the list of possible rational zeros or rational roots. All right. This is a list of possible rational roots, meaning if there is a rational root, and remember, rational roots are just, or rational numbers in general, are numbers that can be expressed as a ratio. So it covers everything from whole numbers to integers to nice fractions, ugly fractions, as long as they can be fractions. They're considered rational roots. All right. So, and you'll see why in a minute. This is kind of like a, I mean, you've already seen how tedious it is, but you'll see why it's archaic in a minute if you haven't already figured it out. So these are my possible rational roots. What I would do at this point is take my p of x function. So p of x, again, 1x to the third plus 1x squared minus 24x plus 36. Strip it down to its coefficients. And then work through your entire list using each one of these possible values, possible rational zeros, as the R value on the outside of synthetic division until you get one that works. And what I mean by one that works would be one that gives you a remainder of 0. Because what I was saying before in last class is if you get a remainder of 0, it means that what you are working with, that number, is a root of the given polynomial. All right. So I'll show you a couple that, I'll show you a couple of cases, but then I'll kind of cut to the chase here because, like I said, with an archaic topic like this and something that can be done easily using technology, I don't want to get bogged down too much. But like I said, it's part of the curriculum, so I want to make sure I cover the topic, but I don't want to get bogged down too much with it. So what I would do is I'd work my way through the list here. So this is my list of possible rational zeros. This whole thing right here, I'll use a different color. These are my candidates. So I'd start with the number 1. Put that on the outside. Drop down my 1 here, multiply the 1 by the 1, I get a 1. Add, I get a 2. Multiply, I get a 2. Negative 22. Add, this one doesn't work. So erase it all. And again, work, like it working means that that last column adds to a 0 because our remainder has to be equal to 0. So then I would try negative 1. Alternate back and forth between positive and negative. So 1 times negative 1, negative 1. Add it together, you get a 0. Times negative 1 is 0. Add it together, you get a negative 24. Multiplied by the negative 1, I get a positive 24. Add it up. That doesn't give me a 0 either. So then I would try maybe a 2. So then 1 times 2 gives me a 2. Add to the 1, you get a 3. 3 times 2 is a 6. Add to the negative 24, I get negative 18. Multiply by the 2. And at long last, it works because I get a negative 36 here. 36 plus negative 36 is equal to 0. All right. So that's great. I got one that worked. Now, like I was saying before, archaic topic. Let me show you real quick. I would type in p of x. You can write f of x, you can write y equals whatever. X to the third plus x squared. Oh, hit the wrong thing. Minus 24x plus 36. Now, nothing shows up on my graph because I don't have a good window. But if I go to the home, I now have a good window. If I'm looking for rational roots, I'm looking for clean x-intercepts. Boom, boom, and boom. -6, 2, and 3. We just got the 2. Right, so that's one of the roots. All right, I'm just going to save this picture real quick. Kind of keep that up here for funsies. There we go. Yeah, so you know going in what the roots are that are going to work. It's going to be the -6, the 2, and the 3. But then you look at this and say, well, how am I going to get the rest of the roots if I have to do it algebraically, if I got to show the work? Well, first off, I mean, any question that would ask you to list the rational zeros, you'd have to do that. I keep saying rational zeros. Rational zeros, rational roots, they mean the same thing. So I go back and forth, but I'll try to be more consistent. Rational roots is what I prefer to say, right? But yeah, we would still have to come up with that list. But then once we have the list, we look at the picture and say, all right, well, we know what the answers are. So magically, I guessed the right one initially. Yeah, like I suspected it was 2. How would I ever know anyway? You know, like it's not the kind of thing that I would ever be able to verify. Right. So then what I would do, I'll check the chat in a second. What I would do is look at this remaining expression and say, all right, because remember the instructions, write each of the following as a product of first degree factors and find the roots. Right. So we'll find the roots first and then go from there. But I started off with something that was power of 3. We performed a division. So our result is going to be power of 2. Then power of 1, then power of 0 as you decline from left to right. This 3 here is an assumed positive, so I'll chuck in a little plus sign there. So this is really the same as saying x squared plus 3x minus 18. All right. Now, if I'm looking for roots, I'm looking for instances in which this function is equal to 0. So I would set this equal to 0 and solve. Now, you know, pick your favorite method for solving a quadratic. However, bearing in mind that the answer could be radical, the answer could be imaginary. That being said, we have the graph in front of us. We know that the answers are all rational. They're all clean numbers. So when I go to factor here, it's going to work out, but you could always use the quadratic formula or completing the square. All right, so my factors would be x plus 6, x minus 3. Set each of those factors equal to 0 and solve. All right, so take each one of these puppies, set them equal to 0, make a little t-chart out of it. And you get x is equal to -6, x is equal to +3. All right. So we have our 3 roots. X would be equal to 2. That was the one that worked using synthetic division. X is equal to -3. I'm sorry, -6, and x is equal to 3. So then the only thing that we would need are the factors, right? So we'd have to write this in factor form. Well, we already kind of sort of have some of it in factor form, because in order to get the x equals -6, we had to have a factor of x plus 6. In order to get a root of x equals 3, we had to have a factor of x minus 3. All right. So we know that we're going to have an x plus 6 and an x minus 3. The only question that remains would be, what about that x equals 2? Well, this comes from x minus r. All right. So that computation of x minus r equals 0 gives us the 2. You're just kind of working backwards here. So this would become x minus 2 is equal to 0. All right. So x minus 2 would be the corresponding factor. Now, what a lot of people will do is they'll just say, all right, I'll just take whatever the sign is of the root and reverse the sign. You know, it was negative, I'll make it positive. It was positive, I'll make it negative. But the product of these three factors would give us p of x, and it's very easy to verify. Just type in y equals factor x minus 2, another factor x plus 6, and another factor x minus 3. Make sure they map to the same location, and you're in good shape. All right. So there's a lot going on with these questions, but a lot of it, I think, is kind of unnecessary because you can pull the appropriate factors just from the graph. I'm sorry, the appropriate roots just from the graph, just like we did with the multiplicity questions. So it's kind of unfortunate, but it is, you know, it is what it is. All right, so we'll do another one. You know, it's not, like I said, it's not pretty, but we're going to kind of cut to the chase and do a little streamlining. So we'll just hop down to number 3. Right. Yeah, because that one's a little jazzier. So we identify the P and Q values. So that's P representing the factors of the constant term, Q representing the factors of the leading coefficient. So I'd say P is going to contain any number that can divide evenly into 15. All right. Now, I mentioned before that the simple way of doing it, but also a very tedious way, is to say, all right, well, what does 15 divided by 1 give you? What does 15 divided by 2 give you? And so on. But you could also use a slider by saying 15 divided by A, you know, whatever you want, whatever letter. And then have that slider go from 1 to whatever the number is, in this case 15. Go from 1 to 15 in 1 unit increments. All right. If you do it like that, then any value you slide to along the way will give you a result of the division of 15, but only by integer values. Well, in this case, whole number values. I'm going to slide this down a little bit. And so you can see, as I move down the line, it's a little bit easier to see. All right. So 1 gives me a whole number, not 2, not, well, 3 does. So 1 and 3 are good. Not 4, but 5 is good. Not 6, not 7, not 8, not 9, not 10. The next one would be 15. So 1, 3, 5, and 15. Now, some of us can do it pretty quickly and easily in our heads, come up with these values, but some of us aren't really there, at least not yet. So just giving another way of handling. All right. Now the factors of 2, that part's easy. I mean, 1 and 2. But bearing in mind, it could be positive or negative. Squiggly bracket game's a little off. All right, so P divided by Q, the list of P values divided by all the Q values. So what I'd have to do is take each one of these P's, each one of these, and divide it by each one of the Q's. All right. So I'll have my plus or minus, but I'm going to take 1, 3, 5, and 15 and divide each of them by 1. But then I'm going to take my 1, 3, 5, and 15 and divide each one of those by 2. So that's 1 half, 3 halves, 5 halves, 15 halves. All right. So this is the list of possible rational zeros. All right. Possible rational roots. Same zeros. Can't stop myself. All right. So I rewrite my function, stripping down only to the coefficients. All right. So I have my P of X is written as 2x to the third plus 15x squared plus 22x minus 15. We know that every exponent is accounted for here. Power 3, power 2, power 1, finally power 0, which means it's okay to go right to the coefficients, 2, 15, 22, negative 15. And then, if this were the Stone Ages, we would resort to what I was doing before. Start with the number 1, see if it works. Then go to the number 2, see if that works, and so on. What we're going to do is a little bit more of a sophisticated approach. So P of X is equal to 2x to the third plus 15x squared plus 22x minus 15. And then we're just going to grab one that works. Nice clean one. So you go across the line here. Any one of these 3 roots are going to work. So pick the one you like the most and go with it. Okay, probably stay away from the fraction, I guess. So I'll go with the negative 3. I'm going to put the negative 3 on the outside. So 2 times negative 3 is negative 6. Add, I get a 9 times 3, and negative 3 is negative 27. Add, I get a negative 5 times negative 3 is positive 15. Add, and I get a result of 0, which is what you get when a number divides evenly through synthetic division. So we're looking pretty good here. So now I'm left with a quadratic. And like I said before, pick your favorite method of simplifying a quadratic. I lost a little hat to the 5 there. All right, so we started off with a cubic. We carried out the synthetic division process once. That means we're down to a quadratic. Power of 2, power of 1, power of 0. Little plus sign there. We can write this as 2x squared plus 9x minus 5. Because we're looking for roots, we set it equal to 0. And factor and solve. We know it should be factorable because we got rational roots. If I'm going to multiply to a 2x squared, makes sense that it would be 2x and x. If I'm going to multiply to a 5, it's going to be 1 and 5 or 5 and 1. put the 1 there, the 5 there. All right, one of them's got to be positive, the other's got to be negative. Do it this way. The outers give me a 10x, the inners give me a negative 1x, which makes a positive 9x, so we're good there. And then, so now we have our factors, so we're in good shape here. So you could actually just pull your factors from this. P of x is equal to this factor, which we were saying before, we just reversed the sign. Instead of x equals -3, we would write that as x plus 3 equals 0, right? So the corresponding factor is x plus 3. Then we have these other two factors that we know are going to work out. And to save yourself time, energy, and effort, energy being the word of the day. Right? So again, energy is the word of the day. We can pull the roots right from the graph and say, oh yeah, I did it in my head. We got x is equal to 1/2 over here. I set that equal to 0. We got x is equal to -5. So my roots are x is equal to -3, 1/2, -5 in no particular order. And so you have it, all right? The root shouldn't be the hard part because you pulled that right from the graph. It's just demonstrating that they are in fact roots of the polynomial. That's where it gets a little tricky. You know, it is what it is. But what we have to do now is tackle a case that involves, I mean, I started this whole journey with a discussion of complex numbers, so we have to tackle one of those puppies. So I'm going to grab a problem from the next page and show you how those problems, or show you how that concept looks. All right. It's pretty interesting. I just gotta find one that's a good one.
It was energy, right?
Yeah, energy.
Okay, thanks.
No problem. Let me just check this real quick. Yeah, so number 10 would be a good one.
So are we still on the same topic or are we going backward here?
No, same topic.
Okay.
So we talk about rational roots again. Now in this case, we don't really have much wiggle room, but we can look at this and say the P is going to be factors of 1. The Q, leading coefficient, is also a 1. So P over Q can only be these two possibilities, right? Plus or minus 1 divided by plus or minus 1, which is going to be plus or minus 1. All right, so we only have two possibilities to work in synthetic division. So that's good news, I suppose. But we're also looking at something that's a power of 6, so that's terrifying. So let's see how this plays out. So I'm going to rewrite this polynomial as 1x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0x to the 3rd plus 0x to the 2nd plus 0x minus 1x to the 0. So 0x to the 1st minus 1x to the 0. All right, accounting for every exponent between 6 and 0. All right. Since there were no terms that had power 5, 4, 3, 2, or 1, those must have coefficients of 0. All right. So stripping it down to just the coefficients, gives us this really lengthy expression. But my rational root theorem tells me that if there are going to be any rational roots, it's got to come from the set of plus or minus 1. Also, took the liberty of putting the graph in. Those are clean roots, so we're in pretty good shape here. All right. So I can put in the 1. 1 times 1 is 1. 1 plus 0 is 1. Times the 1 is a 1. Plus the 0 is a 1. Times the 1 is a 1. Plus the 0 is a 1, and so on. All right, so that's nice and clean. But it didn't get us down to a quadratic. So we're kind of in a little bit of a bind here. All right. I do know that the -1 is also going to work. All right. So I'm gonna do this again. Now I can do this one of two ways. I can pull these coefficients, copy them, and bring them down, and just kind of make a new synthetic division problem out of it. You know, like so. You know, put the -1 on the outside. That's like a lot of extra writing. So what I do is I just build my synthetic division, my next line of synthetic division, right off of the first line. And I'm not the only one who does that. That's the standard way of doing it. Right. So we do it that way, just to kind of save a little bit of space. So pull down the 1, multiply by the -1, you get a -1. Add. -1 plus 1 is 0. Multiply. 0 times -1 is 0. Plus the 1 is 1. Multiplied by the term on the outside, you get a -1. Add. You get back to a 0. You see it's alternating between 1s and 0s. So multiply. Add. Multiply, and finally add. Finally add? No. Well, it would help if I multiplied correctly. So let me just go ahead and do that. All right, 1 times -1. Fun fact of today is -1. So we get this as a result. So looking at this expression and comparing it to what we started with, you know, we got 1s and 0s. All right, that's something. But what we have to keep in mind is that each step of the way, when we do synthetic division, we're reducing our power by 1. So we started off with a power of 6. After one iteration of synthetic division, that gave us a power of 5, so x to the 5th, x to the 4th, 3rd, 2nd, 1st, and 0. I mean, you can put in all your pluses and all that good stuff if you want. But then we did synthetic division a second time. So it would make sense that we're going to reduce our power a second time. So instead of it going from 6 and just staying at a power of 5, we did synthetic division a second time. So now it's going to go to a power of 4. So x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0th. All right, tuck in some positive signs there. And we get, when we clean it up, x to the 4th plus x squared plus 1. All right. So we have two roots, and these roots correspond with factors. So this is x equals 1. That's a root of x equals 1. Its corresponding factor would be x minus 1 set equal to 0. This root is x equals negative 1. Its factor would be x plus 1 is equal to 0. All right. So this is a good opportunity to check your work and make sure that everything's making sense so far. So I'll call this p of x, the original function. I could rewrite this as the product of each of these factors. I got this one, and this one. All right. So I could say y is equal to x minus 1, x plus 1, and then this monstrosity, x to the 4th plus x squared plus 1. Plus 1. I was like, I did it wrong. No, I did something wrong. It just wasn't what I thought. All right. So we're looking at the same graph, which means what I'm dealing with is equivalent. All right. But now that we know that, we would want to be looking at that x to the 4th plus x plus 1 to see if we could pull a solution from that. All right. Whether it's real or imaginary. So I would look separately at y equals x to the 4th plus x squared plus 1 and see what's going on there. Now, if I just look at that function, that 4th degree equation, I'm looking at something that never crosses the x-axis. All right, so that's telling me that there's some imaginaries going on there. All right. Now, it is something that can be solved. It's just not going to be pretty. Let's just put it that way. All right. Any trinomial that's in quadratic form can be solved using the quadratic formula. All right. So you can also do it with completing the square, but historically, I found that most folks don't really like doing that. All right. So I'm gonna use the quadratic formula. So quadratic formula x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. Now you look at this expression with the a's, b's, and c's, and you say, okay, this is familiar, hopefully. But what you're looking at is a 4th degree equation. And you're like, well, how does this really tie together? All right. Well, this applies for quadratics in the general form of ax squared plus bx plus c is equal to 0. All right. So this isn't quite that, but it's got the same structure. So we could actually use it still. All right. So the only issue is we're going to get an x squared out of it rather than just an x. So the modification here would be that x squared is equal to this entire expression squared. I mean, it is an equation, so you can square both sides of it. Okay? That's a valid move. It's a property of equality. Okay? So if I want to apply the quadratic formula here, what I would do is I would say, all right, I got x to the 4th plus x squared plus 1 is equal to 0. understood coefficient of 1 and 1. So my A, B, and C values would be 1, 1, and 1. So I could plug this into my quadratic formula and see where it gets me. Okay, so x squared would be -1 plus or minus the square root. Oh, it's got, this is where it all falls apart. I can't make a radical symbol anymore. Oh, there we go. 1 squared minus 4 times 1 times 1 all over 2 times 1. All right. So simplifying, I get 1 squared, which is 1, minus 4 is -3, so that's imaginary. That's perfectly fine. We're expecting imaginaries. So we get x squared is equal to all that stuff. Now it's at this point where we start really just kind of counting up exponents and making sure we've accounted for everything. Okay? Because what this is giving us is a root for x, but everything actually occurs in complex conjugate pairs. I mean, that sounds kind of terrifying, but it's actually, we're pretty close to having the additional roots. We can clean this up a little bit. Sorry, I get a cramp here. That radical -3, I'm going to rewrite that.
I just got a quick question.
Radical -1 and a radical 3. My internet connection is unstable. I don't know if you yeah, I'm still not hearing anything. Maybe put it in the chat because I'm not catching.
You sound good right now.
Oh, I thought you said you had a question.
I do have a question. I was just waiting until you were good.
Oh, okay.
Are we doing question 9 because I kind of ran out of space, so I wanted to use the left side of the sheet because the back of my notes is the next page since I printed double-sided.
Honestly, I don't know, maybe, but if we do, you could just write it somewhere else, I guess.
Okay.
Yeah, I mean, if anything, we might come back to it for like review or something. So we're looking at, yeah, no problem. So -1 plus or minus this -1 under the radical. That's the same as saying I. So this would be I radical 3 over 2. And so that's what x squared would be equal to. Now, if I want to get x by itself, I would take the square root of both sides. I apply that power of 2, the square root to offset the power of 2. But in applying that, I'm going to create a plus or minus. Okay, so x is equal to plus or minus all of this. And for this question, I think we should just probably, I mean, it's pretty intense, probably just worry about the roots and not so much the factors. But this would be the remaining set of roots for this polynomial function, right? So it's a disaster, but it's our disaster, I guess. I mean, I wanted to show you how bad it could be. And I think I succeeded in that. There's also, the cases where, we've already seen them, or we've already seen them, the cases where it could be really easy. It's just kind of like a mixture of the two ideas, And if you just kind of hang on to that, you'll be in pretty good shape. But our roots, we got the two that worked, which would be a 1 and a -1. And then we have the other, believe it or not, there's 4 more roots in here. They're just complex roots, all right? So, I mean, we could write them all out separately, but it would be a disaster, right? I can tell you that we would have a negative radical with all the stuff inside of it, and also a positive radical with all the stuff inside of it. But each one of the radicals with all the stuff inside of it has a plus or minus. So each one of those radicals actually contains 2 expressions. So from this, we only have 2 real rational roots. The other 4 are imaginary roots, all right? So I gave you the best case scenario, and I gave you the worst case scenario. Let me give you a middle of the road example, all right? So let's take a look at number 11, okay? And that'll be the last one we do tonight. So here's a case where I'm actually giving you one of the roots, but I'll show you that this is the middle of the road. All right. So we have coefficients of 1, 9, 24, and 16. We don't have to use the rational roots theorem because they gave us a 0 of the function. A 0 of the function is also known as a root. Right. So we don't have to go looking for it. They gave us one. So I would put that -1 on the outside, carry through the synthetic division, 1, -1, 1 times -1 is -1. 9 plus -1 is 8. 8 times -1 is -8. 24 plus -8 is 16. 16 times -1 is going to give me a -16. But when I add that to the 16 that's already there, I get a 0. All right. We started off with the power of 3. My result needs to then start off with the power of 2 and decrease from there. I pop in my little plus signs here. All right. And so this becomes x squared plus 8x plus 16. And if I set this equal to 0 and solve, I'll have my other roots. The problem is they're not rational roots, right? Because you're not going to find a pair of factors that are going to multiply to 16 that'll also add to an 8. So what I would do here, to convince myself, is I would type in y equals x squared plus 8x. That's not an x squared. Jeez. X squared plus 8x plus 16. And you see that there's only one unique root, right? I can get, well, actually, dang it. I chose the wrong example. Son of a gun heck. I was like, wait a minute. After I said that there's no way that you can multiply to 16 and add to 8, I started immediately second guessing myself, and now it's right here. Yeah, there's a really easy way to do it, dingus. It's 4 times 4. Anyway, So you get x plus 4 times x plus 4 is equal to 0, and then solve and you get your roots, right? But they say write it as a product of first degree factors. So we're gonna do one more example after this. Apologies, folks. Because I still got to show you the middle of the road example. So we have the root x equals -1, which corresponds to a factor of x plus 1. P of x can now be written as x plus 1, x plus 4, x plus 4. All right. Ay. So let me make sure that this one works out the way I want it to before I actually start doing it. Plus 7x squared minus 19x minus 60. No, those are three distinct roots. 13's not a good one either. Ay. All right, so here's a typo bonus opportunity for somebody. The imaginary root theorem that's written on the top of page 28 shouldn't be on the top of page 28. I'll let you know in a second where it's supposed to be.
Professor, what did you say? Page 28 shouldn't be on top?
Yeah, the imaginary root theorem on the top of page 28 shouldn't be there.
Imaginary.
So should I
It should
reprint
be on the
after
top
class?
Say it again.
So should I reprint another sheet after class? Because you're gonna make a change, I think, right?
Well, I'm not going to make a change to this document. I'm just telling somebody so that they get an opportunity to submit it for typo bonus.
Oh, okay.
Yeah, so that should really be on the top of page 29. All right. So we'll do number 16, and then this will do it for us. All right. So coefficients x to the 4th, 1x to the 4th plus 0x to the 3rd plus 0x squared plus 0x to the 1st minus 1x to the 0. So it's very similar in appearance to the crazy one that we just did a couple minutes ago, but this one's going to be much nicer. All right. So strip it down to its coefficients. 1, 0, 0, 0, -1. Put the -1 on the outside. Bring down the 1, multiply it, you get a -1. Add, you get a -1, 0 plus -1. Multiply, you get a +1. Add, you get a +1. Multiply, you get a -1. Add, you get a -1. Multiply, you get a +1, add, you get a 0. All right. So if I take a look at the graph, y equals x raised to the 4th minus 1, I see here, just like that other crazy problem, they gave us the one root at -1, but I also see that there's one at +1. So I can jump down another level here using a +1, bring down the 1, multiply, add, multiply, add, multiply, add. And what I'll be left with, if we just kind of jump down 2 levels here, so we're going down 2 levels from that 4, that's going to give us an x squared, x to the 1st, x to the 0th with our 0 remainder. All right. Plugging in our plus signs gives us this expression, x squared. You could write it as x squared plus 1 equals 0, but these coefficients are actually going to be pretty helpful because we're going to use the quadratic formula again. quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The coefficients that are listed there, those are nice and helpful because that's telling me the a, the b, and the c. So I could just pop those right in. Negative 0 plus or minus the square root of 0 squared minus 4 times 1 times 1 all over 2 times 1. All right, so I know I have my two real roots, -1, +1. I'm just looking for the other two because if I have a polynomial with a degree of 4, there should be 4 unique roots. Just a question of whether they're real or imaginary. All right, so my x, if I simplify here, the -0 is 0, so plus or minus 0 squared minus 4 times 1 times 1 is a -4 under a radical over 2. That -4 under the radical can be rewritten as the product of -1 and just a plain old radical 4. Product of the square root of -1 and the square root of 4. The square root of -1 is I. The square root of 4 is 2. Put them together, and we're looking at the plus or minus 2i over 2, which simplifies down to just plus or minus I. So my roots here, and like I said, we're not going to worry about factors when it comes to the complex stuff. So our roots would be x is equal to -1, +1, -I, +I. All right. So, like I said, some are pretty easy. The one I accidentally did a couple minutes ago. Some are really hard. You saw really hard. This one's like, I'll say just right, but it's right in the middle. You know, it requires you to do a little bit of work, but the type of work is not really outrageous. It does require some prior knowledge. Quadratic formula is not something that's an unreasonable expectation. All right. In fact, for those of us who are a little iffy when it comes to factoring, like if you've been weak when it comes to factoring quadratics, then quadratic formula is your bailout anyway. Right. The problem is we're dealing with some imaginary values here, so we have to incorporate those into our solutions. Right. So I will ask you to take a look. Really, just I don't want to overdo it. Just numbers 14 and 15. Because there is a lot of problems. Like we don't need to do them all. You know, you could try whatever you want, but these are the two that if you can handle these two, then you're in pretty good shape. You're in very good shape. All right. And then next class we'll get into oblique asymptotes, and then we'll start talking about logs and stuff like that. All right. So let me stop the recording. I hit the wrong thing. Stop the recording.